go. All right. Thanks everyone for coming to Tulsa Lambda Lunch. Thank you for joining us today. We're here thanks to Techlahoma, our volunteers, and our speakers. Techlahoma is a non-profit volunteer-run organization that puts on 39 groups, 2 conferences, and sponsors free local events. We do this to support our mission to advance the grassroots tech community of Oklahoma. Learn more at techlahoma.org. It's extremely important to us that our members feel safe and respected at our events. If you have an issue with someone's behavior at a Techlahoma Foundation event, please let us know via the incident report form or one of the other methods provided on our website so we can take immediate action. If you'd like to get more involved with Techlahoma, go to help-wanted.techlahoma.org to find ways that you can volunteer. If you want to support Techlahoma, you can go to techlahoma.org/donate and sign up for a monthly subscription. We've been streaming most of our stuff via Blixa Project Make It to YouTube or Twitch, depending on the meetup. So thank you, Blixa, for streaming this event. And thanks to Tech Systems for food and meeting space.
Yay.
All right. So today's talk is Recursion Schemes. All about that base case. So in the beginning, there was the humble go-to. When we were all doing non-structured programming. And it was not good. And then came if, then, else, while, and for. And it was structured programming, and it was better. So next ascended the higher ordered functions like map, flat map, filter, fold, reduce. Functional programming concepts that increased readability in a way that if, then, else, and while improved go-to. And it was good. And now, functional programming with bananas, lenses, envelopes, and barbed wire. Okay, there's a famous paper that was about the creation of recursion schemes with this title. But I mean recursion schemes. Okay. And it was awesome. So, what is a recursion scheme? If, for, while are to go to, and map, flat map, and filter are to if, for, while, as recursion schemes are to recursion. This is the best way that I can sum up what a recursion scheme is. It's the formalization of various patterns of recursions so that we don't repeat our code and so we're less prone to make mistakes. And also to hopefully make code more readable, at least if you understand the foundation. In the same way that if, for, while helps improve readability over go-to. So let's get down to some brass tacks and look at some examples. And we're going to be using this library called Drost for most of our examples. There's an alternative one called Matroshka if you're using Scala Z. You can see in the picture here that it's a repeated image. Clever, right? Matroshkas are Russian nesting dolls, so repeated yet again. All right, so here's a classic example of a recursive function. We have the function that calculates Fibonacci. So we have our tail recursive. We got previous, next, sum aggregator, and our go function. We got a lot of stuff going on here. Question though, what happens if we forgot to subtract 1 from this x? Good old infinite recursion, Stack Overflow nonsense. What happens if we forget to call go, or we called go in another place? We'd end up without tail call optimizations. So lots of little gotchas in here. So the biggest problem though is we have a mixing of concerns. We're mixing up how to loop with what each iteration through the loop is supposed to do. So let's revisit this using recursion schemes. So here I have on the screen a algebra and a coalgebra that does the Fibonacci sequence. And then here we have the actual Fibonacci sequence. You can see I put in 10 and we get 25. And we will go back over this, so if I skimmed over it, that's all right. We'll revisit it in a second. But them's a lot of fancy words, you might be thinking. So coalgebra, G-hilo, what the function am I talking about? So algebra is like in arithmetic. It's what we mean when you have some operations on a thing. So literally plus, minus, multiply, and divide. You take two things, you put them together into a new thing. Coalgebra is the dual of algebra. So an example is if like with monads, if you have pure and flat map, with comonads you have extract and co-flat map. So you reverse the arrows. So coalgebras do the opposite of an algebra. If an algebra puts things together, then a coalgebra takes things apart. So you can think of algebras as folds. You're folding values together, and coalgebras as unfolds. With some seed value, you split it apart into smaller pieces. So morphism, another word that I used, that's a transformation from one thing to another thing. This is the simplest way I could put it. In ancient Greek, it means shape or form. So catamorphism, one of the things that I talked about showed a second ago. In ancient Greek, it means downwards or into. So like catastrophe. Okay? Here's an example of a catamorphism. We have an algebra that is putting things together. It takes some list, takes the head, takes the tail, puts them together. I guess I should sum it up. Takes the head and the tail and puts it together. And you can see if I have a list of 0 to 10, we get the sum of all elements in the list. So that's an example of catamorphism. Anamorphism in ancient Greek means up or along. And I've got no analogy for no English words for that, but it means up and along. Okay, so here's an example of an anamorphism. We've got our list and int again. This time we're looking at the int side of it, and I'm expanding out. So when I'm at 0, it's the nil case. When I'm at n, I'm building up. So we can see if I say 10, I've now got 10, 9, 8, 7, 6, so on. We'll go into more of the pieces here in a moment. A hylomorphism, which is ancient Greek for matter or wood, or like hylophobia, which is the fear of forest or wooded areas, I learned. Basically, we use it as you do a catamorphism, then an anamorphism. So you put those two things together. So you build the tree and you tear it apart simultaneously. So here is a set of recursion schemes. Some of you have been in our office, have seen this poster on our wall. We have our folds on this side and our unfolds on this side. So we have kata and ana. You can see each one of these is a dual of the other. A good example is you have histo, or history morphism, and you have futo, as future morphism. We have pre-po and post-pro, so before and after. The hylo is the refold, and then there is the meta, which is the re-unfold. But we don't need to go into details on all these different kinds, but just know that these are solving various different recursive patterns. So if you're doing something that's a little different than your classic kata-ana pattern, maybe there's already one that exists. Like this nice chrono one, which combines a histomorphism and a futuromorphism. And of course, this is where the thing that I always ask people in interviews, just to see their expression, what is a zygohistomorphic prepomorphism? That's where this comes in. It's a combination of a zygo, histo, prepo, morphism, all in the one recursion scheme. Nobody gets the answer, and it's fine. I just like messing with people. Josh is shaking his head. All right, let's revisit Fibonacci and actually go over the pieces, okay? So we talked about the definition of coalgebra. So here's a simpler example of a coalgebra where we're talking about big ints in the context of an option. So this is our natural coalgebra. And the basic pieces here is n is our integer. If n is greater than 0, then we're going to subtract 1 from it. And then this is our base case. This is our exit point. We exit on none. So this stops recursing at none. And then here is the Fibonacci part of it. And don't be too confused by the CV on the algebra. What this is, because there's, as you can imagine, different kinds of algebras. I like to think of CV algebra as carrier value algebra. Each point through the iteration, you have an additional piece of information set up. So here, our option, we have that additional piece of information is an attribute, and this is how you extract that value as you use this symbol. Yes? I should highlight using this little screen over here. Thank you. So this is our value, and then this is the attribute extracted out from it. So at this, we're going to use this here with a histomorphism. And so our histo part is the previous value from recursion. So this is the current value. This is the previous value. So we add the previous value and the current value together with this case. When there's the none case in our previous value, we return 1. And when we're at the none level itself, we return 0. I have a question.
I have a basic syntactic question. What does colon less than mean?
This is the extractor syntax that Drost used to pattern match on attributes. So the type that's in here is an attribute type. And they use this to separate the current value in the attribute from the previous value in the recursion. So it's 1/2 of the attribute and the other half. Because an attribute is basically a tuple. So this is the extractor for that. I understand the first time I looked at it, I was also a little confused. But that's the syntax that Drost chose. I would have probably just used tuples because it would have been easier to read. So in the same vein, if instead of a none here, we had a sum, that's how you get the sum. And this was the previous level of recursion. So this is how you get the current attribute value in the previous. Anyways, so there's the fib revisited. And then here, we're just combining those together into a G-hilo, which is a generic version of the hilomorphism, so that we can use a histo instead of a kata with our hilo. And then here is our ana. And don't worry about this scatter or gather. This is just implementation details and Drost ways of getting the recursion schemes to work. I'll show an even more simplified version in a moment as we derive how this works. And then here is our end result. So you can see our concerns, though, have been separated now. This is the algebra of counting. This is the algebra of adding something with the previous count. That's basically it. And this is putting them together. Let's talk about fixed point. A little bit of a diversion, but important. In mathematics, a fixed point of a function is an element of the function's domain that is mapped to itself by the function. That is to say, c is a fixed point of the function f of x if f of c equals c. Remember that f of c equals c part. Here is fixed represented in the type system. So our type fix of some f that can hold some value. So think of this as a type level function of one parameter. And it is equal to that type level function with fix passed in again with f. So this being a little bit more simplified representation right here. Here's how we're going to use it. So we define some list f, and we'll have a plus a and a plus b. We'll have some nil case, that is, it's a list of nothing. So this is our end of the list. And we'll have a cons operator, where we have a head of a and a tail of b, extending that list. Now right here I've just made a nice, what's called a smart constructor in Scala. And it's for the nil case, we are casting it into the list of a, b. And then a cons, we want this cons to be of type list f, just to make things a little bit friendlier later. So here's how we fix our list. If we have a list f of a, this is going to be the elements in the list. And then some tail element, if we fix it, we can now have what looks like a traditional list of a. So if I put integer in here, I now have a linked list of integers. This part right here is representing the tail, and that's the part we're fixed pointing. So here's a smart constructor for the fixed version and a smart constructor for the cons version. And then the next slide, this should help it make a little more sense. So if I say cons f of 9, cons f of 10, cons f of 7 with the nil, you can see this is the type at the type system level that this is represented at. You can see cons f of int, cons f of int, cons f of int, and then nil. If we use the fixed version of it, it's just list of int. The difference is on the first one, we know at compile time exactly how long the list is. It's like a heterogeneous list instead of a homogeneous list. Each element in the list can be different. Each tail can be different. We can put basically whatever we want because the compiler is keeping track of what each A and B type is at each level. But when we fixed it, we've now taken what wasn't recursive and made it into a recursive. So now we've got this recursive type, and you can see at each level, we've got that fix in there pinning the type. Do you have any questions on this before I move forward?
Can you go back a slide?
I can't go back a slide. Now that's going back too far. We want to go back to this one.
Yes, I just wanted to look at that again. Okay, thanks.
No problem. Here I'm going to hand wave. This is called a traverse. It is how you walk over a data structure, like if you wanted to do a fold of a map. Traverses are also functors, so you can do maps over lists and what have you. Let's look for a second, though, at the implementation. So we've got our list of some element t, which we could think about t as integer. And then the tail is just defined as star here, because traverse needs an f of some empty bracket. I should highlight over here again. So our fold left, if we want to take our list of some t and some a and fold it left, we know that at the nil of the tree, it's just going to be whatever that initial value they're asking us to fold with. Question?
You used the word functor, which I think is probably worth defining.
So the question was, what is a functor? And a functor, in simple terms, is something that can be mapped over. So you can map a function of a to b, and you will now have a list of a's will become a list of b's. All right, so back to traverse. We got our fold left. The nil case is just whatever the aggregate that they passed in, so your zero value. And the cons case is we don't care about the head because folding is happening on the tail part of the list here. And so we're going to call that f, which is a BA to B, and we're going to provide it the initializer, the 0, and the tail to get our new B out of it. And then the fold right is very similar, and the final traverse function here, it is also pretty similar. In the nil case, we're just nilling it, and in here we're having to deal with this G part of the traverse. The main thing that I want to take away from this is when you traverse on our list F, this isn't a list in the traditional sense. This is the head element and a tail element, which could just be another integer. Yes? An applicative is a type of functor where you can take a value and put it into the functor. So think of options. They have a function called pure or sum, and you can take a pure value like a 5 and you can wrap it in the option so you'll have sum of 5. That is what an applicative is. So lists, sets, those are examples of applicative because you can put a single element into them. And then in the case of this traverse function, what it grants us is the ability to take some data structure and some known data structure, in this case a list of f, and some data structure that follows the applicative rules, and then we can run each element from the original data structure through some transformation function into the new structure and get it wrapped. So normally if you just called map on this list and you use this f function, you would end up with a list of g of b in this case. But what we wanted was a g of list of b's. So that's what the traverse gives us. It swaps f for g when you need it. But let's not get too hung up on the details of traverse. Most data structures have it predefined for you. So let's look at this example here where I'm doing the cons f1, 3, and I'm calling the map function on it, which is using that traverse we just defined. This is going to be the 3 in our case, and we're going to multiply it by 2. So you can see our new cons comes out as 1, 6. So we took the tail and we traversed the tail. Now remember, this is not another list, it is an integer, because we don't actually have this defined recursively right now. So this is what the traverse is doing for us, is just letting us generically look at the tail of a current list. And when we later look at trees, it lets us look at the left and the right side of any given tree. In a generic way, we can call some f on both sides of it. So let's put that all together. We're going to define an algebra as putting things together. So if I have some list of a's, for example, substituting a list for f. So I have some list of a's or option of a or tree of a's. I want to get a single a. So list of ints, I get an int. Tree of ints, I get an int. And then a coalgebra is that tearing apart. So I got some seed integer and I want to make a list of all of its prime factors or something. So this is tearing it apart. I'm going to define a helper here for ID coalgebra, and this is basically using that unfix. So I can go from a list to a list. It's the do nothing algebra, and the do nothing coalgebra, and then the do nothing algebra just fixes it. Here is a HILO and its implementation. HILO being the combination of a kata and an ana. So here's our algebra and our coalgebra. This will return a to b function. And this is where the recursion actually comes in. So we're going new function, and then this is the actual function within it. This is the function class. They defined it this way so we can use the this of the function to recurse. So I'm going to take our coalgebra and I'm going to give it our a value. Once I have that a, it'll be in the form of an f of a. Since f is a functor, or a traverse as we defined it earlier, I can now perform map on it, and I'm going to use this function to map the f of a into an f of b. Once I have the f of b from executing this, I'm going to execute the algebra to take the f of b back to a b. So the recursion is right here. That's where we hidden it off. Any questions on this? And don't worry if you're confused. My eyes glazed over the first time I looked at this as well. It took some practice. We'll move on, and if you have any questions, we can always cycle back to this line. So once we have all that together, I'm going to define an algebra that takes some list and an integer. We're going to take the head of the list and the tail of the list. In our case, since the beauty of the recursion scheme is we're only looking at one level at a time, this is not the tree or the list, this is an integer. This has already been summed up for us by previous operations. And we're going to add them together. In the nil case, it's 0. So the way this will look practically is as the recursion happens, the HILO will walk all the way to the leaves for us and will give us that nil. And we'll say, oh, when it's nil, it's 0. So it's going to then construct, using our traverse, a cons f with 0 as the tail, and then the head as that next level down from the previous recursion. So at each level, this will be the previous step, and this is the current step. And we just add them together. So here's our list. You can see it's some fixed cons, nil. When I run it through the high-low, using our nice ID coalgebra that does nothing, we get our sum of function. You can see it's some function of that fixed structured int, and ignore the compiler garbage. And now we'll give it our list, and we get the answer of 26 back. So that is the sum of 9, 10, and 7.
It's definitely the most straightforward way I've ever seen it.
It is absolutely the most straightforward way of adding numbers together. But I'm trying to do a simplified example rather than a super complicated. That way I can boil down and distill what's going on. So let's look at range. So we just looked at algebra, let's look at a coalgebra. In this one, we start off with an integer, and I want to do the counting. I want to make a list starting at that integer. So our input is A, our output is list. When n is 0, this being our base case, we do nil. At any other time, all I'm going to do is I'm going to say, here's the element that I'm putting in the list, and then this is the next step. So the next round, that's what goes here. So next time it's n minus 1, and then n minus 1 again, until we finally get down to nothing. So if we put in our ID algebra that does nothing, and our range algebra, we get our range function. We'll pass in 6, and you can see we have cons 5, cons 4, cons 3, 2. I should highlight with this screen, 2, 1, and so forth. So there is the range operator. Any questions on the range coalgebra that I wrote? All right, let's look at quicksort, because that's always fun. So we're going to reuse some of the structures that we just built up with algebras and coalgebras. We looked at implementation details. You could just import Drost. They have a list pre-built for you to use, so you don't have to write the algebras. You don't have to write the coalgebras. You don't have to write the high-lows. You can just do the implementation. But here we're going to go through, we're going to define our own tree. It looks similar to the list. We have our current element, and we have our current element is A, and the next recursive step is B. So here is our value at the node called data. There's our left, our right, and then you can see the nil case being our leaves. And then here is our traverse, much like the last implementation. We can see there's our left and our right. We're just going to look at the fold left for an example here. So our f of BA, so how we do that is we pass in B in our left. Now we have a B that we pass into f again with our right, and now we have a B out of it. Our fold left looks exactly the same, and our traverse just has to deal with that applicative, but it's effectively very similar. So nothing we haven't seen before with our list. Now let's look at some algebras. We have our tree to list algebra, and I just wanted a way of taking a generic, this is the standard Scala list, not our F list. I wanted to take our tree and flatten it into a list. So when we have a leaf, it's nil. We have the empty list. If we have the branch, we're going to take the left side list that we've already built, which on loop 2 will be nil and nil. We're going to combine it together, left side, that center value, and our right side. So this is going to flatten our tree out. Then we're going to define the split coalgebra. And this takes anything T that can be ordered. So when you remember with quicksort, the idea is you take some pivot, you divide everything to the less than the pivot and the right side of the pivot. So that's what we're going to do. We've got our tree, and we're going to output list. So given the first element in the list, we give it a leaf because we don't have it. Given the nil of the list, we just give it a leaf because we're done. Given some head and tail of the list, I'm just going to lazily define the head as the pivot rather than looking at complicated pivot selection algorithms. We're going to then partition the current tail based on it being less than the pivot. So here's our less than the pivot and our more than the pivot using cat's order from here. We got our pivot, we got our less, we got our more, so that's one level. So this branch has the value and has each of those half lists split into it. Now we've got our two algebras. We're going to combine them together with a high-low. So we take our list algebra that just takes some tree and makes it into a list. And then we have our split algebra, which takes some list and sorts it into a tree based on the pivot. And you can see I took my Scala list, I went to some obscene number, generated a bunch of random values for it, and then here is a subset of them, and you can see we got some negatives, some positives, etc. We'll call our new fancy sort function on that random data, and lo and behold, we have sorted data out of it now. So that's merge sort using a recursion scheme. Let's go back. Does anybody have any questions on how this works?
Other than not having a clue, no. The parts that have already been implemented in the library.
In the Drost library.
Does anything change if you were not doing, like, would you still have to implement on the previous screen, or would that be importable for a tree?
So the question is how much of this was implemented in using Drost versus what we're doing by hand. So Drost doesn't have an implementation of tree in their stock library, but they do have an implementation of list. So what you would have to do to implement a tree in Drost is exactly these two slides we did here. First, define the data structure, and then define the traverse for the tree. I will say Drost has a utility traverse that all you need to do is define, I think it's a fold map function. It lets you define a little bit less than what we did here, but I wanted to show a little bit more detail about what the traverse is doing rather than using Drost's traverse. Plus, I'm using all the code from the previous sets of slides that I hand implemented to kind of walk us through it. But Drost does a lot of utilities. Now, one thing I will also note is this code looks very boilerplatey for traverse, and there is definitely a way to automatically derive this. I did not do that because I wanted to showcase how to write one. And I also didn't want to take the time to figure out which library would automatically do it for me. But there is almost certainly a way to automatically do this because it's very formulaic. Each element here for the left and the right, you could just call that F. And if you define, for example, a quad tree with 4 branches per node, it should be very trivial to generically derive a traverse for that. Any other questions? Oh, so the algebra and coalgebra defined here, the high-low, kata, ana, all of those things that I implemented on the last slides, there is a version in Drost already implemented. There's a few things that Drost doesn't implement that Matroshka does, but that being said, I found Drost to be pretty decent. And the code isn't, it's a little esoteric in places, but each function is very surprisingly short and well composed. So it's relatively easy to follow when you get the hang of it. All right, so let's do something fancier. Let's do a quad tree. So we have what we just looked at. We have a value, we have a left, a right, a bottom left, a bottom right, and our nil. We saw that. We have a traverse. This I'm using Drost now instead of my own code. That way it works better. So here's what I was talking about with their default traverse. All I have to do here is define the traverse function. I don't have to do fold left or fold right. And this is pretty much implemented the same way previous slides we implemented traverse. I'm going to implement a show algebra, and this takes a quad tree and turns it into a list of lists. So take a quadrant tree and flatten it down so that, let me see if I can describe it well. Yeah, so imagine a grid or a matrices. And the quad tree is the top left corner of the grid, the top right corner, the bottom left, and the bottom right. The reason it's a list of lists is because I'm turning the tree of quadrants into that matrix. I'm going to use it for image processing to cut to the chase. Yeah.
Just to clarify, the pipe plus pipe is matrix addition?
The pipe plus pipe here is list appending.
Okay. Is that...
Let's go through this step by step.
Where is that pipe plus pipe defined? Is that part of the library, or is that syntax I'm just not familiar with from Scala?
This is the monad append from the cats library. So given two monads, put them together.
Okay.
Yes. I probably should have just used colon, because that's the list cons operator from standard Scala library. But I'm unfortunately pretty used to using this, so my apologies there. But let's walk through the algebra nonetheless. So we have our nil case, our base case, where we just make it an empty list of an empty list. Okay? Or just a completely empty list. And then we have our case where each quadrant is null, but we have some value. So this is the list of a single value. So if you imagine if I had a quad tree of one single level, then I will have a one row and one column, and that's where I'm putting that value at. Then if I have a quad tree of non-empty lists, so let's think of the case where I have a 2 by 2 matrix. So there's one value here, one value here, one value here, and one value here. What I'm going to do is I'm going to take this value, and it's going to be it's going to be in column 0, 0. This one is going to be in column, it's going to be in column 1, row 0. This is going to be in column 0, row 1, and so forth. And that's what this fancy, I take the left side and I zip it with the right side, and then I append the list together. I'm basically just trying to line up how each of those lists get put into the matrix, or the rows and columns. So this merge was designed to take the top left and the top right lists of lists and put them together, and then I'll take the bottom left and bottom right lists and merge them together, and then I will merge those results together by just appending them. In a moment I will show the output of that, so it will be a little bit more clear what the intent was. Here's a show, and a show is from cats, and it is just a two-string function. So we're defining it as, I got a list of lists and I want to print it out. So we just walk the list, and I'm putting nice little pipes and bars so we can see things nicely. But I'm going to skip ahead and see if I can show one of the... So this is what we're trying to see. This is the representation of that quad tree. So just to kind of skip ahead so we can see what the list of lists was supposed to be. These four are one quadrant. These four are another quadrant. So top left corner, top right corner, bottom left corner, bottom right corner. And then if you look at one level, top left, top right, bottom left, bottom right. That's what we were working on. So let's go back here. So I defined a color. We have RGB. We have some nice additions, divisions, pinning it between two values. Don't need to go into too much detail. It's a color. And then I'm going to define this thing called bounds, which is just a fancy way of saying what the color is of the top left of a quadrant, what the color is at the top right. So this is, given a quadrant, what is the colors at the corners? And the V, in our case, is going to be the current height of our quad tree. From the leaves will be 0, top of the tree will be 10, for instance, if it's a 10 height. So given that bounds helper, this split function takes a quad of, it just takes that one level bounds and divides it up into two levels. So this is going to be our kind of a recursive case. If I have, let's say I'm at height 1, and I have the top left is white, top right is white, bottom left as black, bottom right as black, then this is going to define basically the top left being a light gray, top right being a light gray, as we divide the colors in half. We'll come back to this in a moment after we see the rest of it if you have any questions. This is the noise coalgebra, and it takes a quad tree and some bounds and splits it out. So we start with a bound and we build a tree. And here's the end result. So we take our high-low, we want to noise some bounds value, and we want to show it. So
So I'm giving it some height of 3, some white, black, black, and then I'm going to use our show function from earlier to take a list of lists and turn it into a string so we can see it nicely.
Is the G in front of the high-low, the scheme.g-high-low, is that gather, or what is
The G on G high-low is generic high-low.
Okay.
That's way I can combine a... I was basically just copying it from the Fibonacci sequence from earlier. This can probably be simplified to high-low, show algebra, comma, noise without the scatter and gather. But these are implementation details from Drost. Okay. But given we have this single level, we've split it out now into a height of 3. So the 0 node is going to be one of these. The next level up is that set, and then the third height is this 4x4. This is what we get when we scale that up. We get a nice pretty gradient.
Yay.
This, of course, uses that algorithm to divide by quadrants and then subquadrants all the way down to a single pixel. Okay, let's walk back if anybody has any questions on how that quad tree or any of those algebras worked. I'm getting no questions in the room, so everybody must fully understand exactly how recursion schemes work. That's okay. This was basically meant to be a kind of a taste, let you see some of the power of the recursion schemes, and it seems at first blush to be somewhat complicated. And I won't lie, it is. And it will take a little bit of practice to learn it. But once you start using them, the power, just like when you first started using map and filter and flat map, once you start using them and start getting used to it, I think it increases with the readability in much the same way. And it becomes a bit more intuitive, and it starts becoming a little bit more obvious what's going on. But there's a lot of interesting things you can do with it. I like the quick sort. I think that was a fun example. I wanted to do something like good old Greg does, but I didn't have the time to figure out how to draw much more than a gradient on a canvas. But thank you, Josh. Here's some libraries that you can find recursion schemes in. So I mentioned earlier Matryoshka and Drost. This is the one we used here. In Haskell, there is a official recursion schemes. In Kotlin, their Arrow library has recursion schemes built in. So if you're a Kotlin person and you want to play with them, right there. JavaScript, there are ways to do it, but when you're in a weakly typed language, it's a little bit harder. So there's some examples with Flow or with TypeScript. I'm not going to comment on the quality of these. I just Googled and found the first couple results. I think PureScript and maybe Elm also have some examples of recursion schemes. And anybody got any final questions?
Does Drost support using it without all the Fs?
Does Drost support using it without all the Fs? Do you mean like our list F and our quad tree F?
Yeah.
For their built-in list data structure, I don't believe you have to use list F for much at all, because I think you can just specify it's a list, and it has a bunch of built-in plumbing for transitioning from list to list F and back. That way your high-low morphism, you can pass in a list, fold, unfold, whatever you want to do, and get a list back out. And for the structures that we built with our quad tree, you can define a normal traditional recursive style quad tree where your left and right isn't defined in terms of B for our example, and you can define it as left tree as the actual tree type. And you can use that same plumbing to transition automatically between the quad tree F and your not F version of the quad tree. So you can build it in so that you can hand it a regular style tree. It uses the quad F behind the scenes and hands you back a regular quad tree. But you have to add in a couple extra steps besides the traverse. you will need to define, if you have a fancier data structure than a list F, you'll need to define it. So you'll have to do that initial quad F, you'll have to define the traverse and that plumbing in order to not have to use the F everywhere. But that's what the recursion scheme is all about, is considering just your base case and a single level of recursion and hiding away that concern of how do I do the next step. Question?
Have you ever used this in production code, and if not, would you?
The question is have I ever used this in production code, and if not, would I? And the answer is I have used it in production code. I just did some production code at the end of last week and yesterday to make some modifications to that code to further add some cases. I'm not to get into too much details, but we have an ancestry tree that I needed to walk. It's a recursive deal. Certain cases I need to just shortcut out. Other cases I need to expand the tree further. And I have used both the kata and anamorphism separately but not together in order to do that tree. I'm thinking about and contemplating how I can combine the kata and ana steps into a hilo for additional performance. But I used the G hilo, I think it was actually G hilo M, because I'm also using a monad, because I'm also, as part of the tree walking structure, I have to use a remote data set and a database. So I build the data set from a remote system and have to unbuild it into a database at the same time. So it is, I have used it in production. We're currently using it in production, and it's working rather well, I would like to think. Yes?
How did the code review go on that?
There was some glazed expressions, but I think people understand. Part of the motivation for this talk was to help some of my colleagues further understand the use of the question was, how did the code review go? Sorry, but yes, it's still ongoing. Question?
Yeah, actually, I have a two-part question. A, do you know how the performance of this sort of thing compares against the performance of traditional recursion? And B, is this still subject to Stack Overflow errors for deeply nested recursive?
Two very good questions. Part one, performance. How's the performance on recursion schemes versus traditional recursion? And the answer is, I'm sure it's not as good as traditional tail call optimized recursion, because tail call optimizations will turn into a while loop for all intents and purposes. So there's going to be a performance hit like everything, and so in tightly nested loops, maybe not great if you need the optimization. That being said, when you're dealing with remote data systems, combining them together and then putting things in databases, your bottleneck is not your recursive loop. Your bottleneck is the latency, so it's not a concern for those cases. Part B of the question was, is this subject to the same Stack Overflows that traditional recursion is? And if we walk back, if I can get this thing to walk back to the previous slide, when we defined, let's look at our implementation of hilo, and we can see that we have a call here to this, which is recursively calling this function. And so you would think this would Stack Overflow. And yes, under certain circumstances that it can. If your functor is not defined as stack safe, this will overflow. So if you're using something that is a functor but not also a monad, in the cats library, monads map functions are stack safe. If you call map repeatedly, it's trampolined. So this should not cause a stack overflow if your F is a monad. I believe our default traverse from Drost may also help this be stack safe. Not 100% sure on that. The easiest way to, well, I did attempt to show how far this can go stack-wise in the example of, let's see. Well, here we go. So in the sorting example, you can see the size of this list is pretty dang big. And I used the hylomorphism to put it together and take it apart, and it did not balk at this, but I don't know what the login of this is, so I don't really know what the stack height. So I can't tell you if it would stack overflow. But the easy way around it is that G-Hilo M that I said for using remote systems. That means that each step is wrapped in a monad, then you're guaranteed you're going to be fine. The monads are stack safe. You can also use sync or some other stack safe type as your monad. So you can get around the stack safety part if it even becomes a concern. But I'm relatively confident that it's not a problem. Also, if you looked at the size of that quad tree in this grid, that's a lot of, I think it's like 300 by 300 or something. So that's multiple levels of quads, and I didn't seem to have any trouble there. Any follow-up questions?
One, I missed some part of the presentation.
Please.
Excuse me for that. But are we reinventing something which has been in production a long time? And the reason is, why do we do this?
So when are we talking about the code that I showed today?
Yeah.
There was a paper that came out, and I think I don't remember when was it, functional programming with bananas, lenses, envelopes, and barbed wire. That paper was the invention of recursion schemes, and I think it was in sometime the late 90s, early 2000s when that paper came out. And so that's when libraries started spouting up that implemented those recursive patterns. I don't believe this is a reinvention. This is a formalization of recursive patterns.
Okay.
So this is taking those classical tree walking algorithms, doing depth first searches, or computing things on the leaves of trees, and just making a formalization of the common patterns. To go back, I can show you I believe it was, yeah, it's on the end of this row. So here's the list of formal patterns and different ways to do recursion on these structures. And it doesn't just work for trees, as I showed. It works for lists. Anything you can define with that functor and traverse, you can put through a recursion scheme.
Will you have, if you don't already, will you have a link to your slides on the meetup?
I have published the question was, will I have a link to the slides on the meetup? And the answer is yes. All of the code for the slides, I used a tool called Tut, which takes a markdown file with Scala in it, compiles it, and then produces a new markdown file with the Scala output on each line. That's what the comments are on lines like this one. So I'm using Tut to compile the slides, but I will put the markdown files and everything in my GitHub, and I will put it as a link on the meetup, so that if you want to go back through this presentation. I'll also try to attach those link to the slides, not in the meetup, but also in the YouTube video that this is being recorded as.
If the slides don't include a link to the paper already, you can also
The slides do include a link to the paper. So if you would like to read it, it is here in the references section. The link to functional programming with bananas, lenses, envelopes, and barbed wire. I did try to read it. It's very, very math heavy. I got through page 4 before I stopped understanding most of it, but that's okay. And then this first link here, I highly recommend reading it because it was a very good explanation of walking through recursion schemes. Examples are in Haskell, but I found it to be well written and probably better than I could even explain it. And this is part of what got me into doing the recursion schemes at work. I read this setup. It's like 4 different blog posts for that. It was very good. It actually helped me grok it so that I could use it in production.
Preferable compilation is C++, and is that the code being written for or not?
The code in these slides was written in Scala.
Oh, okay.
That's not to say there could not be recursion scheme algorithms written for C++. It almost certainly could happen. The implementation of type classes and other stuff that you need would be a little more clumsy in a language like C++ and Java than in languages that have support for type classes like Scala and Haskell, but that's not to say it can't be done. Any other questions? All right. Thank you all for coming.